Today we will look at some problems about homework 10. For this problem, we need to find the height h, and we assume that the surface A is a datum. And we apply the energy equation. We have that PA over gamma plus alpha A times VA square over 2G plus ZA plus the pump head HP equals PC over gamma plus alpha C times VC square over 2G plus ZC plus the head loss HL. And things the surface is open to the atmosphere, so the PA equals 0. And at the surface A, the velocity is neglected, so the VA equals 0. And since we said that the surface A is the datum, so the ZA also equals 0. And since at the point C is also open to the atmosphere, so the PC also equals 0. And we know that we assume that alpha equals 1, so alpha C equals 1. And the ZC actually is equal to the H. And we also know the head loss between the A and C is equal to 2 times VC square over 2G. So now we can get that. So HP should be equal to the H plus 3 times VC square over 2G. And according to the mechanical efficiency, we have that the eta equals P output divided by the P input. And we, according to the power equation, we have that P output should be equal to gamma times Q times HP. So now we can get that, HP. The gamma should be equal to, the eta should be equal to the gamma times the Q times HP divided by the P input. And from the problem, we know that the eta is 60%, and the P input is 28,000 watt. And when the water at 20 degrees Celsius, we can know that gamma should be equal to 9790 Newton per cubic meters. And we also know the Q should be equal to VC times AC. And from problem, we know the VC is 3 meters per second. And the AC should be equal to the pi times 0.11 meters square over 4, since the diameter of the pipe is 11 centimeter. So now we can get that the HP should be equal to 16.191 meters. And we know the HP equals H plus 3 times VC squared over the 2G. And we also know the VC is 3 meters per second. So we can get that. Now we can get that the H should be equal to 58.8 meters. So we finished this problem. For the second problem, A, what's the flow direction? From this figure, we can see actually the flow direction is from the right to the left. Since the total head should decrease in the flow direction, and we can see the HGL is decreased from the B to the A. So the flow direction is from the right to the left. And the B, what kind of machine is at A? The machine is pump. Since it can cross a abrupt rise in the EGL and HGL by adding the energy to the flow. So we can see there is a abrupt rise. So we can know that the machine is pump. C, do you think both pipes AB and CA are the same diameters? No, actually the pipe CA is smaller because of the the diameter of the pipe CA is smaller because of steeper the HGL. So we can write the CA for the C. The CA is smaller. And D, we need to sketch an EGL from the system. And we'll sketch the EGL from the B to the A to the C. So from these points, right, and sorry, and is drop to the surface of the reservoir. So the red solid line is the EGL. Since there is a A, the machine is at A is a pump, so we can see that is a abrupt rise. And then since the diameter of the pipe CA is smaller, so the slope is steeper. And then there is a abrupt expansion, so we can see that the EGL is dropped to the surface of the maybe the reservoir. So we finish, and the E, is there a vacuum at any point or region of the pipes? No. Answer is no. There is no vacuum at any point of the pipes. So we finish this problem. For the third problem, A, we need to indicate which is HGL and which is EGL in this figure. And actually, the solid line is the EGL and the dashed line is the HGL. Since the EGL is positioned above the HGL by the definition. And B, are all pipes the same size? If not, which is the smallest? Actually, the pipe AB is smallest. AB. Since from the figure we can see the slope of EGL and HGL is steeper between the A and B, so the head loss will be larger inside the pipe with a larger velocity. For the C, is there any region in the pipes where the pressure is below atmospheric pressure? If so, where? From the figure we can see the pipe BC. The pressure is below atmospheric pressure, since we can see the HGL from the B to the C. The HGL falls below the pipe. For the D, where is the point of maximum pressure in the system? So the maximum pressure is at the bottom of the tank. This one. And for the E, where is the point of minimum pressure in the system? So we know from the BC, from the pipe BC, the pressure is below atmospheric pressure, so it is negative. So actually, the minimum pressure is at the band C. So for the E, it's at the band C. So for the F, what do you think is located at the end of the pipe at point E? Since we can see the HGL is dropped, so maybe there is a nozzle. Sorry. There is a nozzle at the end of the pipes, and the velocity changed, so you can see the HGL dropped. For G, is the pressure in the air in the tank above or below the atmospheric pressure? So it should be above the atmospheric pressure. Since we know the flow direction is from the left to right. And H, what do you think is located at point B? I think maybe there is abrupt expansion. There is abrupt expansion is located at point B, since we can see there is a abrupt drop in the EGL at the point B. So we finish this problem. For the first problem, for A, we need to determine the discharge of the water through this system. So the first, we assume that locate 1 on the water surface, and locate 2 out of the nozzle. So this is point 2, and we apply the energy equation. So we can get for A, we can get that P1 over gamma plus V1 square over 2G plus Z1 should be equal to the P2 over gamma plus V2 square over 2G plus Z2 plus the head loss. And from the problem, we know the P1 should be equal to 0, V1 at water surface is neglected, so V1 also equals 0, and Z1 equals 100 meters, and the P2 also is 0, and the 2 is 30 meters, and we know the head loss HL should be equal to 0.014 times L over D times the velocity in the pipe v square over 2g. And for the problem A, the L should be equal to, because we apply the energy equation at point 1 and point 2, so the L should be equal to 100 meters plus 400 meters. So the L should be equal to the 500 meters, and the D equals 0.6 meter. So we can get that. $100 meters should be equal to V2 square over 2g plus 30 meters plus 0.14 times 500 meters over 0.6 meters times v square over 2g. So we can get that 7 meters, 70 meters should be equal to the v2 square over 2g plus 11.67 times v square over 2g. And we know there is a narrow at the outlet, so we apply the continuity equation to the narrow. So I will sketch draft of the narrow. So at the left side, the diameter is 16 centimeter, and right side outlet diameter is 30 centimeter. And we'll show this is AN and this is A2. So we can get that V times AN should be equal to V2 times A2. So we get that V times the V is the velocity at the pipe, in the pipe. So the V times pi times d square over 4 should be equal to the V2 times pi times d square over 4. So a smaller d equals smaller d equals 70 centimeter, a big D equals 16 centimeter. So we can get that the V2 should be equal to 4 times V. And we also know 70 meters equals V2 square over 2g plus 11.67 times V square over 2g. So we can get that the V should be equal to 7.045 meters per second. So the velocity in the pipe should be equal to this value. And we know the Q should be equal to the V times A. So, and A should be equal to pi times d square over 4. And we know the D is 60 centimeter equals 0.6 meters. So we can determine that the Q discharge is 1.99 cubic meters per second. So we finished problem A, and we need to solve a problem B. We need to draw the HGL and the EGL for the system. So this is EGL. This narrow, so smaller job. And this is HGL. Sorry. So the red solid line is the EGL, and the red dashed line is the HGL. So since there is a arrow, so the velocity increase, so we can see the HGL, the drop. So for the C, we need to locate the point of maximum pressure. So the maximum pressure is at this point. Sorry, I used the other color. So this is the maximum pressure at this point. And for the D, we need to find the point of the minimum pressure. Actually, the minimum pressure should be at this point. Since the pressure at this point is negative, below the atmospheric pressure. And then for the E, we need to calculate the maximum and the minimum pressure in the system. So for the E, the first we need to calculate the maximum pressure, and we apply the energy equation at point 1 and at the location of the maximum pressure. So we have that the P1 over gamma plus alpha 1 times V1 squared over 2G plus Z1 should be equal to the P maximum over gamma plus alpha 2 times the velocity at maximum pressure square over 2G plus the Z location of the elevation of the pressure, maximum pressure, and plus the head loss. And from this figure, we know that the P1 should be equal to 0, and V1 is 0, Z1 is 100 meters, and the velocity at the maximum pressure should be equal to the V, and we have calculated the velocity at the point V is 7.045 meters per second, and the elevation of the P max is 30 meters, and the HL, the head loss, equals 0.014 times 500 meters over 0.6 meters times 7.045 meters per second square over 2g. Since the maximum pressure at this point, so the L also equals to the 100 meters plus the 400 meters, so L is 500 meters. And then we can get that P maximum pressure should be equal to 372.28 kilopascal. And then we need to calculate the minimum pressure, and we apply the energy equation at point 1 and at a location of the minimum pressure. And we have that P1 over gamma plus alpha 1. Oh, sorry, I forgot to say that alpha 1 and alpha 2 should be equal to 1, since the problem gave us that the alpha equals 1 at all the locations. So alpha 1 equals alpha 2 equals 1. Sorry about that. And then go back to this. So P1 over gamma plus alpha 1 times V1 square over 2g plus the U1 should be equal to P mean over gamma plus alpha 2 times V2 square over 2g plus the elevation at minimum pressure point and plus the head loss. And we know the P1 is 0, V1 is 0, Z1 is 100 meters, and sorry, this is not a V2, this is the VPMIN, and we know the VPMIN should be also equal to the V equals 7.045 meters per second, and the Z PMIN should be equal to let me check, 100 meters. And the head loss HL should be equal to the 0.014 times L over D times 7.045 meters per second square over 2g. We need to notice that now the L should be equal to 100 meters, since from this point to this point the pipe length is 100 meters. So now the L should be equal to 100 meters, and the D is also 0.6 meters. So now we can get that the minimum pressure should be equal to the negative 82.7 kilopascal. So we finish this problem. For the fifth problem, we need to find the power generated by the turbine and sketch the EGL and HGL. First, we locate 1 at the upper water surface and locate 2 at the lower water surface, and we also set this the lower water surface is Dayton. And then we apply the energy equation. So we have P1 over gamma plus V1 squared over 2G plus Z1 should be equal to P2 over gamma plus V2 squared over 2G plus Z2 plus the turbo head plus the head loss. And from problem, we know the P1 equals 0 since the P is open to the atmosphere, and the V1 is 0, and C1 equals H equals 100 feet, and P2 is 0, V2 is 0, and the Z2 also is 0 since it is datum, and the HL, the head loss, is 4 feet. Since problem gave us that the total head loss is 4 feet, so we can get that 100 feet equals HT plus the 4 feet. We get that the turbo head is 96 feet. And then we apply the power equation. So we know that power at output from the generator should be equal to the efficiency 8 times P input tutor by. And we know that the P input to turbine equal to the gamma times Q times HT. And since this problem didn't give us the water temperature, so we're showing that the water temperature at 10 degrees Celsius. So the water temperature, we're showing that the water temperature is 10 degrees Celsius, so we can get that the gamma should be equal to the 62.4 pounds force per cubic feet. And from problem, we know that the Q should be equal to the 1000 cubic feet per second. And we know the HT is 96 feet, and eta is 85%. So we can get that the P output from generate the power from the generator should be equal to 503.880 pounds force times feet over second, and it is 61.46 horsepower. And then we need to sketch the EGL and the HGL. So we can start from this point. And then the turbine will cause upwrapped job in the AGL. So there is an upwrapped, sorry. There is a upwrapped job since the turbine. And then still, since there is the upwrapped expansion, so the EGL also will drop to the lower surface water. So this is EGL. And then we'll draw the HGL. So we use the red dash line to represent the HGL. So it is below the EGL, and also there is upwrapped job. And then the HGL will approach the water surface. So the red dash line is HGL. And at the lower water surface, the EGL and the HGL at the same location, at the same elevation at the lower water surface. So we finish this problem. For the last problem, we need to find elevation in left reservoir, and we also need to sketch the HGL and EGL for the system. So the same will locate the L at the water surface of the left reservoir and locate R at the surface of the right reservoir, and we apply the energy equation. We have that the PL over gamma plus the alpha L times VL square over 2G plus ZL should be equal to the PR over gamma plus alpha R times VR square over 2G plus ZR plus the head loss from the L to the R. And based on this problem, we know that alpha L should be equal to the alpha R equals 1, since we assume that alpha equals 1 at all the locations. And we know the PL should be equal to 0, and the VL also is 0, and PR is 0, VR also is 0, and so we know the ZR elevation is 110 feet. And now we need to calculate the HL. So actually the HL, the head loss in this problem, includes 4 parts. And we assume this is A, this is B, point B, this is point C. And we assume that the velocity in the pipe AB is V1, and the velocity in the pipe BC is V2. So the first head loss is in the pipe AB. So we assume that the head loss, the first part of head loss HL1 in the AB should be equal to, according to this equation, so HL1 should be equal to 0.02 times LAB, the length of AB, over the D, AB plus times V1 square over 2G. And from the problem, we know the D1 and D1 and LAB, so it is equals 0.02 times 200 feet over 1.128 feet times V1 square over 2G. And the second head loss is in the pipe BC. So HL2 in BC. So HL, the head loss in the pipe BC to be equal to 0.02 times L, the length of BC, over DBC times V2 square over 2G. So it equals to 1.02 times 300 feet. 2 times 300 feet over diameter is 1.596 feet times V2 square over 2G. And the third head loss, HL3, at the point B. From the figure, we can see that there is an abrupt expansion at the B. So the head loss caused by this abrupt expansion, HL3 should be equal to the V1 minus V2 square over 2G. Actually, this is equation 7.37 in your textbook. And from this figure, also know there is another abrupt expansion in point C. So the head loss at the point C should be equal to V2 minus VR square over 2G, since we know the VR is 0. So we can determine that so HL4 should be equal to the V2 square over 2G. And now we're substituting all of this in this equation. So we can get that the ZL should be equal to 110 feet plus the 0.02 times 200 feet over 1.128 feet times V1 square over 2G plus 0.02 times 300 feet over 1.569 feet times V2 square over 2G, and plus V1 minus V2 square over 2G plus the V2 square over 2G. And then we know the V1 should be equal to the Q over A1. And from the problem, we know the Q is 16 cubic feet per second, and the A1 is 1 square feet. So Q is 16 cubic feet per second, and A1 is 1 square feet. So we can get that the V1 is 60 feet per second, and the V2 to be equal to the Q over the A2, and we know the A2 is 2 square feet. 2 square feet. So we can get that V2 is 8 feet per second. And now we can get that ZL, the elevation at the left side reservoir, should be equal to 129 feet. So it's 129 feet. And then we need to sketch the HGL and EGL. Let me sketch the EGL first. And from this point, so I use the other color, maybe the green. So please. There is at the B there is a abrupt expansion, so the EGL will drop. And then since V2 velocity is smaller than the V1, so the slope of EGL will minor. So EGL, and at the C there also is a abrupt expansion, so the EGL will drop to the water surface. So the green solid line is the EGL. And then I will sketch the HGL. So HGL is dashed line. At point B, there is abrupt expansion, so the HGL will upward little. And then the HGL will decrease to the water surface. So the green dashed line is HGL, and the distance between the HGL and the EGL from the point A to B is the V1 square over 2G, and the distance between the EGL and the HGL between and from the B to C is V2 square over 2G. And we know at the right and at this water surface, the EGL and the HGL at the same elevation. So this is the EGL and HGL. So we finished this problem.